I'm Richard Underwood from the Salt Lake Train office. The following is for general presentation purposes only and does not contain all of the train's required safety and other procedures. For any safety or service procedures, please call us at 486-0500. Thank you. I'm here to give you a little bit of training on your chillers outside or your new chiller. I see quite a few new faces that I haven't seen before. How many people in here actually understand how the chillers operate, or this new train chiller? General. Okay, what I'll do is I'll kind of go through and give you how the refrigeration cycle works on these chillers. The refrigerant in this chiller is R123. That's a low pressure refrigerant, so your suction pressure very seldom goes into a positive pressure. Your condensing pressure will get up to about 15 psig. For most purposes, what we have is, can anybody tell me what the 4 things that are needed for a refrigeration unit? One would be the evaporator. Condenser.
Metering device.
Metering device.
Compressor.
And a compressor. We got them all, that's great. Okay, we're going to start with the evaporator. Basically what it is it's a heat exchanger that removes heat out of your chilled water. We've got an entering, and on most chillers that you'll see, you'll have your entering and your leaving water on one side, and they're right across from each other instead of up and down. In our evaporator, in the center, you're going to see an opening that comes in from your economizer. This opening has little holes in it. Okay, these holes and this little device here is one of your metering devices. It's not what you see opening and closing up above. So what happens is the refrigerant is going to be a liquid, and it goes through these holes and it creates a pressure differential. So that's one of the metering devices that we have in here. And that would be set right down here in the center of your evaporator. If you look on the inside of the evaporator, there's a long piece of channel iron in it. This channel iron has little holes drilled through it the length of the chiller. What happens is, that's what we call a distributor. So this liquid refrigerant that comes through this opening with your orifice device distributes out your liquid refrigerant and vapor through these little holes. It distributes it evenly. Can anybody tell me what type of a system this would be classified as? We have TXV systems.
Fixed orifice?
It's a fixed orifice, or they also call it a flooded evaporator. In other words, all your refrigerant's going to be down at the bottom. And it starts to boil off. Up here at the top of the evaporator, you guys have probably heard us talk about a suction elbow. what happens is the compressor is what's creating your pressure differentials. The suction elbow comes up and you'll see something like this on your chiller. It expands out. On the suction elbow, where it enters, you're going to see something if you was to look in it, I don't know how many people have seen us when we've tore one of your chillers down. But there's going to be a great big opening like this, and it's going to have a little hole in it. There's going to be things that are going to be divided like this. Those are classified as vanes. Now what the vanes do is they'll be fully closed in an unloaded situation. As you need more capacity, these vanes start to open up, and what you would see is, instead of having this triangular thing, you would have just a great big old opening for your refrigerant to go through. Behind these vanes, there's going to be a distributor plate and an impeller. The distributor plate's going to kind of look like this. It's going to have little notches on it for it to distribute out your refrigerant gas. This is the center of the hub. So your shaft goes through this here. Right before that, you would have an impeller. Now what the impeller looks like is, if you look at it from the front, you've got the center where your shaft is, and then it's going to have little things that look like a turbine. On your very first stage, which is right here by your suction elbow, you've got, like I say, right here would be this guy right here, your vanes, and then your impeller would be right here. And on the impellers, your first stage impeller, like I say, looks almost like a turbine, but the openings on it are big. They're bigger openings, and the thickness of the impeller is a lot thicker. So what happens is, when we're spinning, it centrifugally throws it actually is being sucked in or pushed in from the compressor, and it throws the refrigerant vapor out into your second stage. So up here you're going to have we'll just kind of go from the suction elbow. I'm not a good artist. That's where all this stuff is. You're going to see an indentation where it kind of comes down and goes into another volute. There's another impeller in there, which looks just like this. The only thing is, the openings start getting tighter. So what we're doing is we're actually compressing the gas. It's a low pressure gas, and this is what creates your higher pressure gas. As it comes out, we're going to go into another thing that is actually a discharge volute that comes into your condenser. and your compressor is going to be right here. Okay, so what we're doing is we're compressing the gas into a high pressure gas, and this high pressure gas goes into your condenser, and there's going to be a little plate here so that all the refrigerant just doesn't hit the top of the tubes right here, but it sends all your gas, high pressure gas, down over these tubes. And at the bottom in the center, you're going to have something that looks like this. So what happens is your condensing water goes through, it condenses your refrigerant, high pressure refrigerant gas into a liquid. As it goes through, down through your drip leg or your liquid of your condenser, there's going to be another one of those orifices right here. So it's got the little holes, things like that. So actually that's starting to break up your liquid pressure, your liquid refrigerant. It starts breaking it up, and it ties into what we call an economizer, which is that black thing on the side of your chiller, and it's covered with insulation, and it's got a leg. So the condenser's going to, or the economizer is going to come up like this on your chiller, and you're going to see a tube that comes up to this hole. As your liquid refrigerant starts to break up and become a vapor again, it goes through the economizer and it starts breaking it up, and there's another orifice plate up in here that starts breaking it up into a vapor, and the vapor that's actually been broke up will go back into your second stage volute, which they call an economizer, so that it doesn't have to send all the gas and refrigerant back through down into your evaporator. At the same time, you're going to have another leg that comes off that will tie into your evaporator, which completes the cycle. So you'll have your orifice plate here in the evaporator. So there's actually about 4 orifice plates in here for your metering devices. Your compressor, you're going to see 3 lines. They're going to come off here. The center line is what we call a refrigerant cooling line. What happens is in your oil sump, which is down here underneath the condenser, the oil sump actually has a refrigerant pump that comes off the liquid line of your condenser. On this sump there's a refrigerant pump. So that's going to pump liquid refrigerant up to this line right here. On this line here, there's going to be a little orifice plate in there. Does anybody know what this orifice plate does? Okay. What this orifice plate looks like is, we'll just kind of give a general idea of what it is. What happens is your liquid refrigerant gets up here, and it's pushing the refrigerant through that little hole, and it flashes. When it's doing this flashing effect, basically what it is it's actually flashing and creating cool gas to go over the motor windings. So that's how we get our motor cooling on this. As the gas is cool, we get the same effect. These lines come back down. These are, we've got entering going this way. Entering refrigerant, and then it leaves going out this way and goes back down into your evaporator and your condenser. first stage impellers or your first stage vanes, we have two stages of vanes. One's your first stage, which is right there by your suction elbow. And you'll see an actuator, you'll see a long arm on there that opens and closes that set of vanes that I was talking about. But on your second stage, there's another set of vanes in there that will actually open and close simultaneously as your first stage. And that's what your actual capacity control is on it. On this particular chiller, it's different from your others just for the reason that we have the oil sump down at the bottom. On this oil sump, what we're doing is we're creating, we have an oil pump in there that will pump oil to your rear bearings and your front set of bearings. Your front bearings, where I showed you we had the volute that goes to the condenser, compressor comes through here. There's going to be a set of bearings right here. And actually they're a smooth bearing, and what it does is the smooth bearing feeds the front of the motor on the shaft, and then there's a set of ball bearings back here on the back that the motor or the compressor runs on. So we've got an oil line that'll come up here and drop in on the head for your front or your back bearings. There'll be another oil line that'll come up and go in and feed these bearings. So in general, that's what we're getting as far as how the oil is distributed through the chiller. Now also at the same time, we have refrigerant and oil that wants to mix. There are special seals in each one of the components to keep the oil from becoming massive so that the oil and the refrigerant will pass okay. Everything's going to return back down from another line here down into the oil sump itself. And then on the back of this discharge, there's going to be another line that will come back down into the oil sump also. That is basically the only difference between this chiller and your other two chillers that you have. The only other difference that there is on this chiller, we have what they call a flow gauge. You've got little meters up on the suction elbow. And it's situated about right here, or here's your evaporator. It's situated about right here, which is a set of gauges. Now these gauges are taking your inlet water pressure and your outlet water pressure on your evaporator and the condenser. And what it does is it takes and figures out calculations that'll give you tonnage on what your chiller is actually doing. And it'll also, if set up, can load and unload the chiller by capacity. I don't know how this one's actually set up, so I can't tell you for sure, but we can set it up either way. You're aware of the new panel that we have, which is the Adaptive U panel. It's a very good panel. It's got a lot of capacity in there. I don't know how many of you have gone out and played with it, but you can actually go into a graph bar, hit graphs, and it'll show you how your chiller's running. It's got little graph lines. It'll tell you how your compressor's loading and unloading, what the approach is, oil pressures. It's got everything there that you can watch a graph bar on. Has anybody ever used that graph bar at all?
Usually quite a bit.
Yeah. So it's a nice tool to have. Does anybody know what I mean when I talk approach? Okay. What approach is it's what your saturated leaving evaporator water, or your saturated evaporator refrigerant versus your leaving chilled water temperature is. Usually on an approach, we like to see anywhere from 0 to 4 degrees approach, which is telling us whether we're low on refrigerant or whether we have low water flow or something like that on the chiller. We also have a condenser approach, which is the leaving water versus your condenser saturated water temperature, saturated condenser refrigerant temperature. When we see that approach get up around 5 degrees or more, we suspect one of a couple of things, which would be foul tubes, dirty tubes, or water flow. It also could mean that we have excessive air in the chiller. Now on your chillers, we have what they call a Purifier Purge. On this purge, on your condenser, there's going to be this little machine up here. Okay. I'm a very bad artist. Here we've got a compressor that's sitting up there, just a small little compressor, and a fan in behind, and what we've got is a great big long tube on it. And what happens is we have two lines that come off the condenser and they go into here. Okay, what happens is we're taking condensing vapor, which would be your high pressure vapor, and we're bringing it up into this tube that's got little copper tubes in there. And what happens is, as the refrigerant vapor comes in, this little compressor is connected so that we can chill these lines, this copper line, and as it starts to chill, we get the effect that the vapor is going to condense into a liquid. Now, if for some reason you've got air in there, it's not going to condense and your refrigerant level is going to stay low. In that case, what happens is the suction line on this little compressor over here starts to drop in temperature. Once it gets down to about 18 degrees Fahrenheit, what happens is it turns on what we call a purge pump up here on the top, which goes out to a vent line. At 18 degrees, it's going to remove all those non-condensables and send them out into another tube that we call a charcoal filter. So these non-condensables will go into this charcoal filter. There's a heating element in it that will boil off any of the refrigerant vapors in the charcoal and dump it back into the evaporator so we're not losing refrigerant. And then the non-condensables go out. As we lose our non-condensables, this refrigerant level is going to come up like this, and the suction temperature on that compressor is going to raise. When it hits 22 degrees Fahrenheit, it shuts off that little pump that's up here. So if you see this fan running all the time, don't get alarmed. But if this little purge pump up here is continuously running, we're getting purge time on it. In other words, we've got a lot of non-condensables in it, which means that we need to start looking at doing a leak check. Some of the things that can create problems with your chillers running is like non-condensables, like I mentioned. Water flow is a very good, it's a major problem if the flows aren't within specs. Sometimes you'll get the water flow going to a point of where your refrigerant pressure will go sky high and the chiller will start going into a surge. The same thing will happen if there's non-condensables in it. Now what a surge is it sounds like somebody's just hitting the brakes on the chiller and it starts making a loud squealing, squirching noise. You guys have had that with this chiller from what I understand. And I haven't gotten into all the details of what's gone on it. I was told that it's just not working the way it needs to in the heat mode. So, other than that, I don't know a whole lot about what's going on it, so I can't really tell you a lot about it. If you have a slow chilled water flow, it's going to pick up more heat, and your refrigerant temperature is going to drop. It'll drop like a rock, and you'll start to have a very low load condition, and it'll probably start screeching also. So it's just from low loads. It also can be from too much air in the chiller that will create these problems. As far as maintenance, basically what we like to do, Train has taken a stand that we don't change the oil in the chillers every year anymore. What we do is we take an oil sample once a year, and we change the refrigerant filter and your oil filters. What you want to be aware of is you want to make sure that your contactors are clean, that the contactors don't have, or the contacts themselves don't have any pitting in them or severe pitting in them. This is crucial because the contactors themselves can freeze up and create detrimental damages to the compressor. This chiller over here is running on 460 volts versus your other two chillers from Train that are on 4160. Can you tell me difference or the reason why we've got 4160 versus 460 volts? What happens if you have a high voltage? What happens to your amp drop? It goes down. A 460 volt chiller will have higher amp drop than what a 4160 would have. 4160 seems like down here there's been a few problems with it where we've gotten open rotors. That's probably one of the determining factors why we went with the 460 volt chiller this time. I don't know what the problems are, but for some reason we've had open rotors on both chillers over here. But I think that the problem's been eliminated. Do I have any questions here that I can answer for you?
What does it mean to load up the chiller? You're trying to load,
Okay.
put a load on it to make it more efficient?
Okay, what we want to do, we like to see the chiller run fully loaded. It runs more efficiently. What happens is you want 45-degree water temperature leaving the evaporator and 55-degree water entering. A lot of times if you can get the load, if you've got, let's say, 65-degree water going in and you're still trying to make 45-degree water, what you've got is those veins that I was talking about that looks pie-shaped. They open up.
They modulate, or?
They modulate open and closed. So they're going to open up fully, and when it opens up fully, what happens is your compressor starts working harder. So you're actually giving it more capacity. So instead of being unloaded, there's no capacity there. All it's doing is just purring along doing nothing. Full load, everything opens up, compressor works harder to compress the refrigerant that's going into it. So did I kind of answer your question there?
I think so. Like the veins just modulate to
Yeah.
create a false load. Is that?
Yeah, well, not to create a false load. What it does is it sees a capacity where the water temperature is warmer, and that's entering water temperature. So it goes through the controls saying, hey, at 200 tons capacity, I'm not making it. I need to open these veins up and get more refrigerant going through the compressor to make it load up. so that the more refrigerant that's going through it, the harder the chiller's working and creating, it's actually cooling it down. So everything for load and unload is done with these inlet guide vanes. It's really hard to describe if you haven't seen what the vanes look like, but like I say, they're just 10 pieces of metal cut in triangles, and on the outside of them there's little knuckles, and as the actuator opens up, those pie-shaped pieces, they actually open up, and instead of having a small hole like this, you can have a great big hole like this for refrigerant capacity.
Yeah, aperture.
Right. So that's what we're talking about as far as loading them up.
So what happens when those vanes don't work? Say if they're stuck open and you don't have a load, or a very small load.
What would happen is you'd have a heck of a problem. Your refrigerant temperature is going to drop. It's going to drop like a rock. But if there's something that, the only way that would happen is if you opened them up fully and they got locked into that position. Picture an airplane where you've got your air going through the turbines. If you didn't have any opening there, there wouldn't be any air coming out the back, okay? If it's stuck fully open, what you're doing is you're sucking in all this refrigerant, and it's going to work hard. It's going to work really hard, and you're going to watch your saturated refrigerant temperatures drop like a rock, and you'll also see your chilled water temperatures drop. Once you get down to, let's say the chiller's set for 45 degrees, there's a set point that will take the chiller out, it will take it offline when it gets down to about 36 degrees. That's the safety that it has on it. A lot of times I've seen where this actuator that actually opens and closes those vanes, a pin may break and those vanes go closed and one set of vanes will open up and you have no cooling capacity. I mean, you'll be at 55 degrees or 65 degrees and you're not making any refrigerant. You're not cooling the water at all. So that's something that you can watch on your maintenance and walk through, is watch to make sure that those actuators are moving up and down as needed. Anybody had any problems with the chillers that you want to talk about?
We've heard that screeching before on our Yorks,
Okay.
up on the cooling tower.
Up on the cooling tower?
Well, no, at the York. but
Oh, it was due to the
on-
cooling tower?
Yeah,
Because the condensing water was too
too
hot?
hot, yeah.
Yeah. That'll happen on these also. If your cooling tower temperature gets too high and it gets out of spec, you will see a screeching noise. So that'd probably be one of the first things you want to check is what your entering and leaving water temperature is. These chillers are set up for high pressure. They shouldn't be screeching or anything until they get over 15 psi.
Usually what's been happening at 15 psi is it just shuts itself down. It doesn't even start surging.
It just shuts it down, huh?
It just shuts down on the safety switch in there. I guess is what it is. It just shuts off and get the alarm notification.
Uh-huh. Okay. That'll be something that I can go back and talk to Wes about. That thing, the high pressure cutout should be set higher than that, with it being a high pressure vessel for heat recovery. I don't know whether he's done anything as far as adjusting that or not. So that's something I can talk to our office about.
What should it be set at, Jim?
Generally, high pressure cutout is set at 15 psi. Now that's on the condenser.
That's what I'm referring to as the
Yeah.
condenser.
Your condenser shouldn't get any higher than 15 psi, but on these chillers, they're made to where they should go above that because you're trying to use the heat off the machines. Now you hear about ruptured guards and ruptured discs. They say that they'll blow at 15 psi. Well, that's true, but in a running state, Your evaporator is always going to be below 15 psi. It's going to be at a negative pressure. If for some reason let's say we had a fire in here and the chiller wasn't running, more than likely the heat from the fire would blow the rupture disc and cause the refrigerant to go outside. We have rupture guards on these. What the rupture guard is it's a little disc in there that'll pop, and it's got a spring on it that at 15 psi it's going to allow the refrigerant vapor to leave the chiller, and once that refrigerant pressure's gotten down to 13 psi, it will reseat itself. But you'll see a little pressure gauge on there, and it'll start reading what the pressure is inside the vessel. So if your chiller's at a negative 8 inches of vacuum, it's going to show a negative 8 inches. Or if it's at 6 psi, it'll show whatever's happening in the evaporator. Okay, I was asked to come back in and see if I can answer some questions as far as maintenance, or if you occur some problems on your chillers. Some of the main problems that you may run into is going to be your water flow issues. If the water flow is going too slow or going too fast, the faster the water flow goes, the less heat it's going to pick up. If it's slowed down a little bit, it's going to pick up more heat and reject it out. The main thing that I've seen around here has been water flow issues in the past. You may see oil pressure drops. If your oil pressure gets down below 12 psi, the chiller won't stop and it won't run. A lot of times that problem is due to oil filter being plugged up, or also it could be that you're low on oil. Another problem that I've seen with the chillers is the chiller won't start because the oil is too cold. The first thing you want to do and look at would be to see if you've actually got an oil temperature above about 110 degrees. When I set up a chiller, I usually set it so that the chiller will engage the oil heater at about 120 degrees and maintain that temperature. The reason I do that is because a lot of times the oil temperature will drop down and it'll get down around 100 degrees and you've got to wait for the chiller to start back up. So that's one of the things that I do try to do when I do a startup is I like to maintain at least 115 degree oil temperature while the chiller's running. If for some reason you see that the oil pressure's dropped, we need to look at these things like your oil filter. There is actually an oil regulator on the side of the oil sump that we can adjust and bring the oil pressure up. I very seldom see the sensors go bad on these as far as reading oil pressure differential. A couple of things that I've seen is we've had leaks. Most generally you'll find a leak around the economizer or on your suction elbow. It's good to keep those tight. Do it at least a couple times a year. Just go through and go around the flanges and tighten those up. You don't want them super tight, because what will happen is the oil on the gasket will start to squeeze the gasket out and create a bigger leak. The suction elbow, I think they've pretty well got that straightened around as far as leakage on those. In the past they have leaked a little bit here and there. From what I can see though, they've changed the way they want us to, and the way they do the O-rings on the new chillers. What they've done is they've done with an O-ring on the upper half that goes to the compressor section, and then they've used this a white cork tape that they put on there to keep it sealed, and I haven't had any problems that way. They've also had an O-ring that you install that you put a special sealant on when you install it, and then it has to be torqued down at the right torque specs. Some of the things that you want to also look at is make sure that all your terminals are tight as far as in your control panel and your starter panel. Take a look at your contactors and your wires to make sure that they're not discolored. If they're discolored, that's a sign that the terminals could be loose. You're getting too much heat on that particular wire or contact. So that's a couple of things that you need to look at. If you run into a problem, you need to call us. What we'd like to see is give us all the information you can. Give us what the water flow is, your pressure drop across your chiller barrel as far as the water. What's your pressure entering? Is it 20 pounds entering and 15 pounds leaving? So that we can get a kind of a calculation of what the chiller's actually doing. Same thing on your condenser. Check your entering and leaving water pressures. Tell us what your approach is. On that adaptive view, it'll tell you exactly what your approach is while it's running. If it's on your condenser and it's 15 psi, we'd say you've got foul tubes.
Is it referred to as an approach?
Yes.
You see approach in this value?
It is actually considered an approach. Another thing that we look at is what we call lift. It's the difference between your evaporator pressures and your condenser pressures. What we like to maintain is about 20 degrees. That's 20 degrees between your leaving chilled water temperature and your leaving condenser water temperature. So let's say you're at 45 degrees leaving evaporator water temperature. We would like to see the leaving condenser water at least 65, if that makes any sense. What that does is it creates the lift that we need for the pressure differential for your chiller to run correctly. Sometimes what will happen is if we don't have that lift, you'll start stacking refrigerant in your condenser. The condenser will actually keep the refrigerant in there, and the refrigerant going into your evaporator starts to starve the evaporator, which will give you a low refrigerant temperature alarm. I haven't really seen that problem around here at all. Your condenser tubes, they've been immaculate on the other two chillers that I've seen. They're immaculate. You guys have got a fantastic system. So, very seldom do I think that we'll have any problems with the tubes. Most of it would be water flow, which is your valves, your isolation valves on your entering and leaving condenser and evaporator. You may find that the chiller's starting to trip out on high head pressure, which is high condenser temperature or pressure. First thing I would do is look and see if that actuator is actually open and you have water flow going through the condensers. Same thing on your evaporator. If you start getting low refrigerant temperature or low chilled water temperature, check your actuators to make sure that they're open. Because that's some of the biggest things that I've seen down here that's created problems. Does anybody have any problems specifically that they have seen or need to touch bases on?
Our York chillers get a lot of alarms on high heat sink, high temperature heat sink. Trains
Okay.
don't have those, do they?
They would if it was a VFD drive. The York chillers are tripping on high heat sink. I'm thinking that maybe we've got a water pump or we've got a restriction in the glycol that goes through the VFDs themselves. So that's something that we should probably come out and check, or if we're getting it, there's a reason why. It's got to do with the water going through the VFDs. You won't have to worry about a heat sink on the 3 train chillers. Okay, out here in the chiller room, remember when I talked about the orifice plate going into the evaporator? That's situated right down there. It goes into the evaporator right there, right down at the bottom of the chiller.
is that channel iron that I was telling you is a distributor plate that goes all the way the length of the bottom of the evaporator. This is your condenser right here that we were talking about. Up here is where your discharge line goes into your compressor, or goes into your condenser from the compressor. The little plate that's right here along here. And then you've got tubes the length of the chiller. What happens is a hot discharge refrigerant hits these tubes and condenses down into the bottom of your condenser. At the bottom of your condenser, you see this little leg right here? That's your liquid refrigerant. It's a high pressure liquid refrigerant at this time. There is your first, inside right there is where you'll see your first orifice plate to break down your refrigerant. As it breaks down, it comes through here and up and about this high into the chiller. Got another orifice plate with some screens. Comes through, comes up this line right here. Goes back into your second stage of your compressor section. When I was talking about the purge itself, this bigger line is above your liquid refrigerant. Goes in here, goes along that line, and it comes into this tank right here, which has a copper line in there where the refrigerant cools the R123 refrigerant back into a liquid. As it goes through there, and it's liquid, refrigerant returns through the spinner dryer and back down into your evaporator. This line here usually runs about 10 psi. As the liquid level raises up in here, refrigerant comes through this line, goes through the filter. If the liquid level is down around in here, there is a temperature sensor right here on the suction line of this compressor. This compressor, this is just a condensing unit is all it is. It doesn't run on R123 at all. It probably runs on R134A. As this suction line right here gets down to 18 degrees, it'll turn that pump on. See that little fan up there? That's a purge pump. That will purge the non-condensables into that tank that's in the back. Purge it through there. And there's charcoal down on the bottom of the crank release heater on it. As that pump comes on, there's a set of solenoids in the back that open and close, allowing the non-condensables to go out to this line right over here, which is that big line going up. That's your pin line. Okay? Right here is what we were talking about as far as the oil sump. This is one of the things that's different than on your other two chillers. They put it down here, and what we've got is we've got your refrigerant line that comes in right here. That's your refrigerant pump right there on the outside. On the back side of that, you've got your oil pump, which is sending your oil out to that line up there on the compressor. Sends it out to there with your roller ball bearings. It also goes into the front of the compressor, which I'll show you on the other side, which also feeds and lubricates your bearings there. When I was talking about your refrigerant cooling on your chiller, there's your line right there. See that little flat piece of metal in between the flange and the compressor? That's the orifice plate that I was talking about that creates a flashing effect. It cools your compressor. This little line with the 4 bolts on it, there and there is your refrigerant return. This line right here, that's your oil return. As the oil goes over the bearings, it's down into the bottom of this plate and goes down into this line, which returns back into your oil sump. The same thing on the front bearing. There's your other line on the front bearing. Something that I didn't bring up when we was in classes, we've got what we call dual eductor tees. These dual eductor tees create a pump. It's actually a pump. It takes your high pressure off of this line right here. It comes down and it creates a pump. The purpose of these dual eductors is it'll take your liquid refrigerant off the evaporator and off your suction cover and return it back to the oil sump. So it's returning refrigerant and oil as it mixes. As the oil heater in the oil sump heats up, it boils off that refrigerant. So what you have left is a full supply of oil. Let's go over to the other side of the show. The air separator and the non-condensable, why would you constantly have to worry about removing air? Once your sealed system, you should be, and you think it'd be done, you don't have to worry about it. That's a good question. What happens is the chillers are sealed tight at startup. But from time to time, with going from a cold cycle where the chiller's been off for a period of time, where it starts running up, a lot of times the rubber seals and things will start to break loose and create a leak. When we see purge time on the purge counter go up significantly, that's when we start to do a leak check. You can always check your counter on the screen over there and see how many minutes of purge is in 24 hours. Train says that if it purges 10 minutes a day or less, you're okay. It's not uncommon. Although I like to see it purge a lot less than that.
So does that compressor always run then?
We have 3 modes on this purge. One mode is on, the other mode is auto. The auto mode will only run the purge, which you can see the little fan running right now. It'll only run when the chiller's running. We have an adaptive mode, which the chiller the purge will run either in the on cycle or the off cycle. It takes a period of runtime that the chiller's been running, calculates it, tells the purge when it needs to come on, and shut off. Right now the purge is in the on mode. It's really unnecessary. If the purge is in the on mode, it's going to run all the time. So I prefer to put it in the adaptive mode. So it'll just run as needed. And to answer a little bit more on your question, if we get non-condensables in the chiller, it can happen because it's in a negative pressure. When it's sitting idle, it can be as much as 10 inches of vacuum. So it can suck non-condensables in, which in return can create acid and oil and refrigerant ventilation.
Yeah, I understand if you're in a vacuum, you got a leak, it's going to go in and run out.
Right. The other difference on this chiller versus your other 2 chillers is this little system right here. to the controls, telling the chiller whether or not to increase the capacity or decrease the capacity of the chiller, if it's set up that way. If not, it's just an information for you. We talked about the rupture guard. This guy right here is your rupture guard. Right there where you see my pointer, there's a ruptured disc. It's an alloy steel that will break loose at 5 psi. Or I mean 15 psi, excuse me. Once that breaks loose at 15 psi, there's a spring with a relief valve right there. That spring opens up, relieves all the pressure up into the drum inside. At 13 psi, that spring reseats itself. That way you're not going to lose your low charge. When I was talking about a suction elbow, this guy right here is your suction elbow. Your evaporator, low pressure vapor. Pressure goes up, goes through the suction elbow. So right here, which is your vanes. That's your first set of stage of vanes, which is for capacity control. It doesn't have anything to do with the refrigeration process at all. It's just capacity control. So if you need more tonnage, that little arm's going to move down. It's going to open up those vanes. About right there inside will be on the end of the shaft, and there's going to be your first stage impeller. That's that impeller that looks like a turbine. It has the big openings. It goes through and goes to the distributor plate, which is right behind it, which sends the refrigerant vapor around into your second stage. On that second stage is where your second stage impeller is. It actually takes the first stage refrigerant vapor, sucks it in through the little hole, sends it out through the top hole. That's a vapor. As it goes through that, there's another set of vanes right there. These vanes are on a flat plate. It's just on a flat piece of sheet metal. And they open and close according to what this guy's doing here. They work simultaneously. It's run off with your little actuator right there, which is receiving the signal from your camera. As the refrigerant gas is compressed, it comes through this last balloon right here. See that? It sends it over to the condenser as a high pressure vapor. As it condenses, it goes to a high pressure liquid, and then going through the orifice plates becomes a low pressure liquid versus vapor. On the top of the evaporator, right here, there's a screen on it, the length of the chiller barrel. That screen is what they call a mist eliminator. That mist eliminator breaks up any liquid droplets inside the chiller so that you're not getting liquid refrigerant up into here. The distribution plate is down on the very bottom of the chiller. And that looks like a channel line with holes drilled in it all the way down the length of the chiller, which distributes the refrigerant evenly. Just one in the evaporator is all. None in the condenser. Talked about oil lines. There's your oil line for your first stage, or for your front bearing. They're right there. Goes in through the head. And then goes directly onto the bearing chiller, the motor will run at 3,600 RPMs all the time. What creates your capacity is these two here. Now we do have chillers out with VFDs on them, variable frequency drives. What happens is they start up and run at 38 hertz, and this actuator will load up. This is this guy here. Vanes and everything will open up all the way. After it gets to full load operation there, the vanes are out as open as far as possible, the VFD will start to speed up the compressor itself. As you don't need the capacity, these vanes will start to shut back down, and the motor speed will drop back down. And usually, in a running condition, they run 45 to 53%, more or less. Or I mean, 53 hertz of the 60 hertz. Other than that, I think that's everything we've covered. Do we have any more questions I can answer?
These propellers on the scoop, the ones you're talking about, those ones were flat pipe.
Right there where that thing is, that's a set of inlet guide vanes. That's the pie-shaped ones. That's what opens and closes. It goes from a small hole up to a great big hole. Behind that is the ones that look almost like a turbine. It's got a small opening here, and if you look to the side of the impeller, great big openings, which sends the refrigerant around and sends it into the next impeller, which is smaller. It's smaller on the intake and smaller on the thickness of the impeller itself, which creates the compressor. The impeller on the motor cap is up there. On this, the impellers are on the shaft of the motor. The inlet guide vanes are not. That set of vanes is not on the shaft, and that set of vanes is not on the shaft either. The only thing that is on the shaft